Welcome back in the literal sense to CS300 Introduction to Algorithms. And today we're going to resume our discussion of graph algorithms, more specifically for algorithms revolving around connectivity properties of graph, both qualitative and quantitative connectivity properties. So let me fire up the slides. So what you see here is our kind of taxonomy of connectivity problems for graph. We'll consider more complicated problems, more involved problems later, starting at the end of today's session. But let us first recall the different connectivity properties. First, there's the qualitative connectivity. Can we get from a given start vertex S to a given target vertex T at all? Yes or no is the answer to this decision problem. On a more refined level, this is what is indicated here. What is the shortest path? So provided that it is possible to reach T from S, we may ask how fast can we reach T from S, which amounts to the question of what is the shortest path, and more generally, what is the lightest path if we assign weights to the edges in addition to simply counting the number of edges. We also assign we may have weights assigned to the edges. And in this case, the question boils down to what is the lightest path, and more precisely, what is the weight of a lightest path, because the lightest path in general may not be unique, so it doesn't really make sense in the specification to ask for the lightest path, because in general there is not the lightest path, but there may be several lightest paths, whereas the weight of a lightest path is always unique. So this is the quantitative version of the qualitative connectivity property. From given start vertex to given target vertex. And the next variant that we consider is where there's one start vertex S given, and we're interested in the weights of the lightest path to every other vertex. So not just one weight, but many weights are the output to this specification of the second problem. And the difference is that there may be, and actually it will turn out to be, a more efficient algorithm for the second problem than simply repeating the algorithm for the first problem. That's, of course, one way of solving the second problem, by repeating an algorithm for the first problem for every possible choice of T. But that incurs a cost which multiplies the cost of the original algorithm by a factor of n, running it repeatedly, while there may, and actually there is, a more efficient way that solves the second problem at the less cost, not multiplying the cost by this additional factor of n. And this is extends further to the third problem, where there's not even a start vertex given in input, but all pairs of vertices, start and target, are to be output by the algorithm, more precisely the weight of shortest path from any possible start vertex to any possible target vertex. That's the third problem we're going to consider. And in all these problems, we restrict to certain kind of weighted graphs. Namely, we consider shortest path or lightest path on graphs with non-negative edge weights. So, because when the edge weights are non-negative, then shortest paths are automatically simple paths. Simple path is a path which does not visit any vertex repeatedly, and that simplifies our algorithm design and our cost analysis. So this is what we're going to do. Negative edge weights can lead to some paradoxical cases, namely negative edge weights can lead to negative cycles. That is a cycle in a graph, which when traverse the negative edge weight actually results in less weight of the graph, right? That's a paradoxical thing, right? Usually intuitively, when pursuing more edges, then the weight should increase, right? But if we have negative edge weight, then pursuing more edges can actually decrease the weight. And thus, if there's a negative cycle, then repeatedly repeating that cycle can make the weight arbitrarily small and negative. And this is a paradoxical problem. So this is something we deliberately want to avoid in the specification, again, supporting my emphasis on the point that specification is a very important part before proceeding any algorithm design that is easily neglected when just memoizing algorithms. The important prerequisite is the specification. Second remark is it is now no loss of generality to actually restrict to positive edge weights. So that's a subtle point. For the first, we restrict to non-negative edge weights to avoid paradoxes. It is a considerable loss of generality to consider only non-negative edge weights deliberately, because that avoids all the paradoxes. Whereas once we have restricted to non-negative edge weights, additionally restricting to positive edge weights, so that means avoiding edges with weight 0, that is no loss of generality algorithmically and conceptually, because if there's an edge with has weight 0, then we can simply remove that edge and by merging the vertices that it joins, right? So if we have two vertices that are joined by an edge of weight 0, then proceeding back and forth between these two vertices does not increase the cost at all. So that's the same thing as simply merging the two vertices into one vertex, which is easy to do algorithmically. And thus we have in this way removed one edge of weight 0, and we can do that repeatedly. And thus after linear number of steps, we've gotten rid of all edges of weight 0 and only decrease the size of the problem and end up in a graph where all edges weights are indeed strictly positive. And this is what we're going to suppose for the rest of this chapter, actually, to simplify the analysis, because it is no loss of generality algorithmically. A third point to emphasize is it's a crucial property that we will frequently use in the correctness proof of the algorithm that we design. And if we have a shortest path from S to T, and that path visited some other vertices, let's say V1, V2, Vk, Vl, then any segment of that path, let's say the subsegment from Vk to Vl, is again a shortest path. That's an important property of shortest path under the hypothesis that we only have positive edge weights. So that's already an example where the previous two hypotheses enter. And if they do, then they have this property that sub-segments of shortest path are again shortest path. And this is a property that underlies many of the algorithms that we have and will consider. Namely, when searching for shortest path, means we can kind of find shortest path by growing them, by starting with shortest path for other vertices, then maybe not the ones we're interested in, let's say vertices Vk, Vl. So although we may be interested in the shortest path from S to T, we can find algorithmically such a shortest path by kind of growing a given shortest path from Vk to Vl for appropriate vertices Vk to and Vl, and then trying to grow that shortest path. Okay, so that's a recap of the problems. And then we've discussed Dijkstra's famous algorithm for solving shortest or lightest path problem, the least weight problem in weighted graph. And so, yeah, I'm not going to recall the details of the algorithm, but let me emphasize again that the algorithm employs a priority queue. That is a data structure which allows to extract a node, an element of least weight, and to decrease the weight of or the key value of any element in that queue. It does not need to be able to increase, because that's not what Dijkstra's algorithm uses. So in a sense, Dijkstra's algorithm is actually, if you look at it, it's a meta algorithm, right? Because it works with any kind of priority queue as underlying data structure. That's the benefit of abstraction, of information hiding, of object-oriented algorithm design. And depending on how we implement that priority queue, the correctness of Dijkstra's algorithm will be unaffected, but the performance may in general be affected. So the performance that we analyzed here of Dijkstra's algorithm is asymptotically n times the cost of an extract min operation plus m times the cost of a decrease key operation. And what is the cost of extract min and what is the cost of decrease key? That depends on how the priority queue is implemented. A naive implementation using an unsorted array results in linear cost n for each extract min operation and constant cost for each decrease key operation, meaning that in this case, Dijkstra's algorithm becomes as cost n squared quadratic plus O of m. And since m, the number of edges, is always less than n squared, the overall cost is quadratic O of n squared. But using, in case the number of edges is less than n squared, if we have a sparse graph, that's the terminology, then it is beneficial to use a more advanced data structure for the priority queue one, where extract min is cheaper. And maybe decrease key can be a little bit more expensive. For example, in Fibonacci heaps, something we'll discuss in CS300 advanced algorithms, extract bin operation can be, and decrease key operation can both be implemented in logarithmic cost, resulting in a Dijkstra's algorithm now having incurring cost O of n log n plus O of m log n. And even more advanced data structures, such as Fibonacci heap, can a binomial heap result in actually computational cost of Dijkstra's algorithm O of n log n plus O of m without an additional factor. But anyway, that's far ahead, just to kind of cross promote and to keep you interested in all these upcoming very interesting algorithms and data structures. And so, yeah, the baseline is Dijkstra's algorithm is a meta algorithm whose correctness works for any implementation of a priority queue, but whose performance depends on how the priority queue is implemented. And we've ended last lecture by discussing the correctness of Dijkstra's algorithm. And again, that's one of the strengths of computer science as opposed to electrical engineering, that we're focusing on proof-based approaches also to computing, and a rigorous mathematical proof of the correctness of Dijkstra's algorithm. And to this end, we've observed first the possible comparison between two quantities. So one quantity, in order to state the correctness of the algorithm, one quantity is the distance output by the algorithm. This is what is stored in the array D, right? So D is an array indexed here by all the vertices in the graph, right? And I should emphasize here again that Dijkstra's algorithm originally designed to solve the first connectivity problem given a start vertex and given a target vertex. What is the lightest path? It actually already solves the second problem. Given only one start vertex, it determines the weight, the distance, the lightest path to any other target vertex T. So there's no need to repeatedly run that algorithm for every possible target vertex T, so that the algorithm already solves the second problem without incurring additional cost. Yeah, but returning to the correctness issue, so yes, the observation is that we have these two quantities. One is the array of distances from fixed start vertex to any other vertex T, including V, for example, here. That's the output of the algorithm, the internal data structure. And on the other hand, we have the mathematical quantity T, the distance from S to T as given here, from S to T or from S to any other vertex. So these are the two things we need to compare. We talk about the correctness, and correctness means that both quantities agree. The mathematical weight from S to any other vertex T or V, and the algorithmic array is indicating the known distances, the best known, the shortest known distances from S to any other vertex. And the first important observation is that the algorithmic version is never less than the mathematical counterpart. And let's first observe why this is the case. This can be seen by using the loop invariant, right? So initially, the array is initialized with value infinity everywhere, right? And that definitely is at least as large as the mathematical distance, right? Mathematical distance may be infinite if its vertex is not reachable, but it definitely is never more than infinite. So initially, it's kind of proof by induction. Initially, the algorithmic distance is greater or equal to the mathematical distance. And now let's check in the induction step. When is the algorithmic distance improved? The algorithmic distance gets only improved here when calling the decrease key operation of the priority queue. And when it is called, when the decrease key operation is called, it's called with argument d prime, where d prime is calculated here. And d prime is, as you can see, calculated in such a way that if the previous best distance from S to U plus the edge weight from U to V is better than the previous distance, calculated distance from S to V, then it is replaced by this new quantity. And that is correct. That maintains the loop invariant because that indicates that the this value indicates that there exists a path, right? By induction hypothesis, this is that means this quantity means that the algorithm has calculated this quantity as an upper bound to the mathematical distance, right? Algorithmic distance is greater or equal to the mathematical distance, and it has this edge. So combining this implicit shortest path, lightest path from S to U with this edge indeed results in a path with this new edge weight, so that whenever the algorithm performs or decreases value in the array, then this is supported, this is guarantee that there exists a path, and existing a path means that the distance, where the distance is indeed greater or equal to the mathematical lightest distance. So that means that indeed throughout the calculation of the algorithm, the array of distances is never less. It is always supported by the existence of an actual path with that weight, and therefore cannot be less than the optimal mathematical but algorithmically possibly unknown lightest path. So to summarize, the first thing is what we've just proven by induction over the number of iterations of the algorithm is this loop invariant. The distances maintained in the array of the algorithm are always greater or equal to the mathematical distances. Of course, the mathematical distances are by definition the length of a shortest path, and the distances maintained in the array are supported by some path attaining that distance, and therefore must be greater or equal to the least distance. So that's a first part of the correctness proof, the first inequality, that the distances maintained always satisfy this inequality, greater or equal. But for correctness, the claim is that this is actually after the execution of the algorithm, this becomes an equality, right? So we proved that this inequality holds initially, and that this inequality is maintained throughout the execution of the algorithm, and therefore the inequality also holds after the execution of the algorithm. And the crucial part that we know, look in it more closely, is that actually after the execution of the algorithm, this inequality has become an equality. And to prove that claim, let's do that by contradiction, right? So actually, this is a nice exercise in basic mathematics, right? So proof by induction is what we've just done before, right? And now we practice a proof by contradiction, right? Elegant, right? All the example of Dijkstra's algorithm. So proof by contradiction, we suppose that this, after the execution of the algorithm, this inequality is strict for some vertex v, right? So what we want to show is that this inequality becomes an equality for all vertices v. And so the contraposition is that there exists a vertex where this remains a strict inequality, as indicated here, right? So let's suppose that for some vertex v, even after the execution of the algorithm, this is an inequality. And more generally, let's consider the set of all vertices where the algorithm purportedly, hypothetically fails, where set of all vertices where even after the execution, this is still a strict inequality. And let's call this set M. And so the hypothesis that we want to lead to a contradiction is that this set is non-empty. If this set is empty, then we're good. Then that means that there is no vertex, right? So if this set is empty, then that means there is no vertex v in that set, and that means there is no vertex where the inequality is strict, and that means that all vertices have this inequality, actually an equality. So for contradiction, let's suppose conversely, suppose that this set of possible counterexample vertices is non-empty. And now we're going to lead that to a contradiction based on how this algorithm proceeds. Okay, so the first observation is that this non-empty set is a finite set. Well, obviously, right? If we have finitely many vertices, and the minimum of a finite non-empty set exists. So we emphasize two properties: the minimum of a finite and non-empty set. The minimum of an empty set does not exist. Some people say it's plus infinity, but anyway, it does not exist. So that's really where our hypothesis for the indirect proof enters. the hypothesis that this set is non-empty and therefore this minimum exists, and let's call the value of that minimum delta, abbreviating, and that's actually a finite real number, not infinity, because the set is supposed non-empty. And then what are we going to do then? Well, since this is a finite set, that means that this is a minimum as opposed to, let's say, an infimum of an infinite set. And since it's a minimum, it means that this minimum is attained. That means there exists a vertex which attains this distance. Let's call this vertex V. Right? So here the emphasis is such a vertex exists. Yeah, we're doing a lot of mathematics today, right? Nice, isn't it? You may have been expecting a lot of computer science and programming, and fair enough, this is part of the new homework assignment, programming. But algorithm design and analysis is a lot about mathematics and discrete mathematics, and that's what we're doing here. Actually, proof theory, proof by induction, and now proof by contradiction. So let's continue our proof by contradiction of the correctness of Dijkstra's algorithm, and continue with the argument. So let's consider a lightest path mathematically from our fixed start vertex to this purported least smallest counterexample vertex V, right? So every vertex V in this non-empty set M is a counterexample to the correctness, purported correctness of Dijkstra's algorithm. And here we have kind of selected the least counterexample. This is actually something common also in computer science, right? When you find a bug somewhere and you report the bug to the developers, you're kindly asked to find the smallest counterexample that exhibits that bug, not thousands of lines of code, but the smallest counterexample, so that the developer can kind of trace the cause of the bug and identify, debug. And that's what you kind of do here also mathematically. The B we consider is kind of a least counterexample vertex because that's one with least weighted distance from S, where the algorithm purportedly fails to produce the correct distance. And now we consider the shortest, or more generally, a lightest path to this vertex. And by the property, right. And since this is a counterexample, it means that any shorter path, since it's the minimal counterexample, it means that any shorter path satisfies this equality, right? So that's an important point. That's the reason why we consider the least counterexample, because it means for any shorter path, the algorithm is guaranteed to yield the correct answer, to yield the correct least distance, where for any shorter path, this inequality becomes equality. And in particular, that holds for the subpath for the segment from S to U, right? This is, remember, we talked about this important property of shortest path, that segments, subsegments of shortest path are again shortest path. So if we take here shortest or lightest path from S to U, V, and consider the initial segment from S to U only, that is a shortest path. Actually a shorter path than the path from U to V, because the final step from U to V by our other hypothesis has positive weight, right? Remember, we only considered at weights which are strictly positive, and here the final step of this lightest path from S blah 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 to U, and then from U to V, therefore has strictly positive weight, which is added to the weight of the initial path from S to U, or put differently, the weight of the shortest path from S to U is strictly less than the weight of the shortest path from S to V. And therefore, since it's a minimal counterexample, it means that this shorter weight is calculated correctly by the algorithm, so that V is kind of the first, right, the minimal counterexample where the algorithm purportedly fails. And in particular, this distance to U is therefore, by assumption, calculated correctly, and this distance is strictly less than the distance we consider here. This is where the induction or the hypothesis enters, that we choose a minimal counterexample. Okay. And since this distance is calculated correctly, it means that when the algorithm gets to consider the distance from S to V, that final vertex, that means at that stage, the distance to U has been calculated correctly and is less, and therefore will be extracted, right? That's a property of being a priority queue, extracting the vertex with least key value, and the key value of this vertex U is therefore strictly less than the key value of the vertex V. You see these properties, right? Which means that the extract min operation, whenever it extracts the vertex V to calculate its distance, it will have first extracted the value, the vertex U. And once the vertex has been extracted, it, by the construction of the algorithm, its distance in the array will have been calculated and fixed and will not be changed anymore. That's another important property of the algorithm, right? So each vertex gets extracted from the queue precisely once, right? So the loop gets executed precisely once for each vertex, and once it has been extracted, then its distance in the array may or may not have been improved in this loop, but after that, for every extracted vertex, its distance will be correct, and therefore yield a better distance to the target vertex V, which is a contradiction to our hypothesis that the algorithm produces a larger distance to the target vertex V than it does than mathematically required. So this results in a contradiction to our hypothesis that this set here is non-empty, which means the set must be empty, and therefore there cannot be any counterexample vertex, which is exactly what we wanted to prove. So this concludes our indirect proof for the correctness of Dijkstra's algorithm. Two nice application of mathematical proof strategies: proof by induction and proof by contradiction. And now we know that Dijkstra's algorithm is really correct, which superficially is not at all obvious, right? I mean, algorithm is famous because, well, because it's efficient and because if it's correct. If it were not correct, would not be very famous, right? Anyway, so yeah, that concludes our discussion of Dijkstra's algorithm. And now we want to proceed to our third type of connectivity, quantitative connectivity, namely the all shortest path. So we've discussed previously the shortest path from a given start vertex to given target vertex T as solved by Dijkstra's algorithm. Then we've discussed the problem of calculating shortest path length from a given start vertex S to all target vertices T, which is also solved by Dijkstra's algorithm at no additional cost. And now we want to consider the final variant where the algorithm is supposed to produce all shortest paths for all possible pairs S and T, which we can solve by repeatedly running Dijkstra's algorithm. So let's analyze that. So Dijkstra's algorithm considers the start vertex fixed and deals with all possible target vertices T. So in order to additionally cover all possible start vertices S, we can repeatedly run Dijkstra's algorithm for every possible start vertex S, which since one execution of Dijkstra's algorithm has this computational cost, running it repeatedly means multiplying that computational cost with an additional factor of n, right? So that the computational cost becomes n squared times the cost for extract min plus n times m times the cost for decrease key operation in the priority queue. And well, if we take our standard unsorted array, naive implementation of priority queue, that means that the first part becomes n squared times n, which means n cubed, plus n times m times constant, which is n times m, which is okay. But if we have more advanced implementation of data structures, then we maybe want to do better. Also, let me emphasize that Dijkstra's algorithm is kind of a complicated algorithm to implement. So what we see here on this slide is actually a very simple algorithm, which may or may not perform better than Dijkstra asymptotically. But on small graphs, before the asymptotic kicks in, it will definitely have its advantages. And this is the so-called Floyd-Warshall algorithm, famous because of its simplicity. So again, we initialize our array, but now it's a two-dimensional array, right? Remember the goal of this this variant of the problem is to calculate all shortest distances between all pairs of vertices. So when the previous Dijkstra, we had the start vertex fixed, and the array would only need to consider all possible target vertices, which is a one-dimensional array. But here we need to consider all possible target and all possible start vertices, which means that there is that this can be represented as a two-dimensional array, which is initialized with the value given by the adjacency matrix, which may include the value infinity, right? Or if an edge is present, then a finite value. And again, the Floyd-Warshall algorithm will, like Dijkstra's, gradually decrease entries in this now two-dimensional array whenever it finds a path that is better than the previous path. So the Floyd-Warshall algorithm consists of 3 loops that are nested, loops that only run over the vertices, interestingly, not the edges. The edges presence or absence is implicit in the adjacency matrix. And whenever for any possible choice of this triple of vertices, u, v, w, and what the algorithm will consider is path from v to w via u. Observe the important but subtle order of these loops, right? So the algorithm does not consider paths from u to v via w, nor does it consider paths from u to w via v, but really what it considers is paths from v to w via u, although the order of the loops is kind of different. So path from v to w, if the current shortest path weight in the array is worse, then first going from v to u and then from u to w, then by triangle inequality, we can, and the algorithm will improve that. So it's kind of, again, gradually minimizing the length of shortest path for as far as the algorithm can be sure that they exist. So so let's already talk a little bit about correctness of this algorithm. Again, we have this kind of loop invariant that the distance is maintained algorithmically in this array by the algorithm will always be greater or equal to the mathematical distances, because whenever such a change, well, it is true initially, right, here, and whenever such a change happens, then that change is kind of justified by the existence of an algorithm, of a path with that improved weight. And namely, in this case, whenever we have a path from V to U and a path from U to W with this weight, then by combining, concatenating this path, one arrives indeed at an improved path whose weight is this. Okay, so that already concludes our half of our correctness, namely the inequality that the distances calculated by the algorithm are always greater or equal than the actual mathematical distance. And again, it remains to argue that after the execution of the algorithm, they actually become equal. So initially they are greater or equal. Through the execution, they remain greater or equal. And the claim is that after the execution, they are actually equal. Okay, I'm not going to repeat, this is a kind of similar proof as we had on the previous slide for Dijkstra's algorithm, so I am not going to repeat that. And also the computational cost analysis is kind of trivial. By simply looking at the algorithm, we have 3 nested loops, each running over all vertices, n vertices, so that the computational cost is n cubed, because the loop body is kind of simple, has constant cost, and also observes that the algorithm does not need any of the advanced data structures that Dijkstra, for example, needs with this priority queue. There's no priority queue, no other data structures. It's really a very simple algorithm, and that's, I guess, what makes the algorithm famous. Its running time is as good as Dijkstra for some graphs, more precisely for dense graphs, for graphs which have n squared edges. So not necessarily all edges must be present, but asymptotically, almost all edges must be present. And then the computational cost of repeating Dijkstra n times is comparable to the computational cost of Floyd-Warshall algorithm. However, when the number of edges is less than n squared, asymptotically, strictly, considerably less, like n log n, for example, then actually repeating Dijkstra's algorithm is preferable to Floyd-Warshall. That's an important but subtle point with which I want to conclude and close our discussion of the connectivity problems for graphs and optimal algorithms that solve these connectivity problems. And so far, we have been discussing graph problems concerned with paths and of linear subgraphs. What we now proceed to is some more complicated subgraphs, namely trees. So this was about shortest, about minimal weight graph paths, and next we consider minimal weight trees. These are called minimum spanning trees, namely. And after that, that may be actually next lecture, not for today, we will consider even more general kind of subgraphs, maybe in flow problems. But yeah, without further ado, let's consider the minimum spanning tree problem. And as usual, we start by focusing on the specification. Right, what is the minimum spanning tree problem? The input is, as usual, a graph, more precisely an undirected graph. This is important here. That is a graph represented by a symmetric adjacency matrix, which may or may not be weighted, and still we focus on non-negative, or more precisely, strictly positive edge weights. That's kind of the answer of the quiz question. We consider strictly positive edge weights. So that's the end of time. Let me type that. Right. So the answer to the quiz is we consider strictly positive edge weights. And the reason was given before. So, and now the goal is to find a minimum spanning tree that is a spanning tree of least weight. So what least weight is, this is something you know. For a subset of the edges, T, just add all the weights of the edges in this subset rather than in the entire graph. So that's the weight of a subset of edges, but I need to tell you what is a spanning tree. Because then you know what is a least weight spanning tree. What is a spanning tree? Well, it is a tree after all, and a tree, as you recall, is one way of putting it as a connected graph without cycles. That's a tree, a connected graph without cycles. Well, you have in your mind probably a different conception of a tree. If you look out the window, you see trees and something like this, which is great for intuition, but for mathematical specification and for rigorous proofs, those trees that you see outside of your window are not really suitable. So we will proceed with the notion of a tree to be a connected acyclic graph. And what is a spanning tree? A spanning tree is a tree that connects all the vertices of the original graph. So a spanning tree is a subgraph that contains all vertices of the original graph, but not necessarily all edges. Only sufficiently many edges so that the resulting subgraph is still a tree that is connected and acyclic. Actually, it's not a loss of generality to drop the acyclicity condition, because if we have a spanning graph of least weight, then this will automatically be a spanning tree of least weight. We'll repeat that important observation. If we have a connected, yeah, that's important one. If we have a connected spanning subgraph, then that will be a spanning tree. What's the subtle difference? The difference is that a tree, in addition to be a connected subgraph, is also required to be acyclic, contain no cycle. So why can we drop that condition of being acyclic for minimal spanning connected graphs? Well, because if a minimal connected spanning subgraph has a cycle, then we can simply drop one edge of that cycle and still have a spanning connected subgraph, right? That's kind of a redundant edge then. And by dropping that, the edge weight will only decrease. Remember, that's one of the reasons why we would restrict to strictly positive edge weights. So dropping that edge weight, this is what result in even a better subgraph. And considering that will repeatedly result in a tree. So it's no loss of generality to calculate minimum connected spanning subgraph of least weight. And here you see a picture. Okay, let's consider that picture. In this picture, you see vertices A, B, C, D, E, F, G, and I. And you see edges. You see two types of edges, weighted edge. Every edge is labeled with a positive integer. Positive integers I keep emphasizing and keep emphasizing and questioning why we do so. Restrict positive integers to positive weight. So And the two types of edge correspond to fat edges and thin edges. All edges are, in this example, part of the original of the input graph. That's kind of the specification, that's the input graph. And the fat edges, these are the edges of the output graph, namely of the minimum spanning tree of least weight. Let's verify that. Let's verify the property that this is a tree first. The fat edges form a tree. The original graph is not at all a tree, but the fat edges form a tree because they connect all vertices. Every vertex is reachable via fat edges only. And there's no cycle. Yeah, as usual, for any minimal connected spanning subgraph, you don't see any cycle among the fat edges. And the interesting property is that these fat edges form not just a spanning tree, but a spanning tree of least weight. And to verify that, that's kind of complicated, right? At least naively, it involves considerable efforts in checking that there's no other spanning tree of less weight, strictly less weight. And finding such a better spanning tree naively would require considering all possible other alternative or competitive spanning trees, of which there can be exponentially many, right? So every spanning tree is a subset of the edges. How many subset of the edges are there? Well, in the worst case, there can be exponentially many subsets, the power set of all edges, right? And that's, of course, algorithmically terrible. Testing exponentially many subsets as possible candidates for a spanning tree and then taking the one of least weight, that's not suitable algorithmically because it incurs exponential cost. So that's not a good way of actually calculating a minimum spanning tree. And let me emphasize again, when we say calculate the minimum spanning tree, I should be more precise, calculate a minimum spanning tree, or even better, calculate the weight of a minimum spanning tree. Of course, minimum spanning tree itself need not be unique, but the weight of a minimum spanning tree is unique. Okay. So yes, to summarize, now we have introduced and specified and provided intuition for you guys with the problem of minimum spanning tree. Now we can proceed to consider algorithms that can calculate minimum spanning trees in polynomial time. That's the point. We have our naive algorithm for calculating minimum spanning tree that runs in exponential time by trying all possible subsets, but we want to do so in polynomial time. And one of the algorithm that achieves that is Prim's algorithm, which is kind of convenient because on Tuesday, you have probably received a homework assignment asking to implement Prim's algorithm. So let's discuss Prim's algorithm. And here's the not even pseudocode, but even a higher level description of the algorithm. And the basic idea behind Prim's algorithm is to grow spanning trees, minimum spanning tree. So the observation is that a single vertex is trivially a minimum tree, but not necessarily spanning, right? It doesn't span that graph, right? And what Prim's algorithm does is it gradually adds edges to a minimum tree so that the tree will span larger and larger parts of the original graph. And at the end of the execution of Prim's algorithm, the entire graph will be guaranteed to be spanning. So the loop invariant of one loop invariant of Prim's algorithm is that it maintains a subset of the edges that forms a tree of least weight, but not necessarily spanning yet. but spanning increasingly large subparts of the original graph. So we have here this tree that consists of a single vertex initially, which is chosen arbitrarily from the graph. And then we grow that tree edge by edge, one by one. And the important choice of Prim's algorithm is which edge to add. There are so many edges. So if there's an initial tree, you can choose any vertex in that initial tree to add maybe a new edge, any vertex to an edge to a vertex that is not yet part of the tree. Okay, that's important. We cannot add an edge to between two vertices that are already part of the tree, because that would create a loop, right? And so the choice should be made among the edges with vertices that are not yet in the tree, as indicated here. And among these edges, Prim's algorithm chooses an edge that has least weight. Let me say it again. Prim's algorithm connect in one iteration of Prim's algorithm. It considers all edges that connect the tree to some vertex which is not yet part in the tree, because adding that edge grows the portion of the original graph that is spanned and reached by the tree. And among these candidate edges, one is chosen with minimum weight. And then add that to the tree, to the subset of edges that is maintained as a data structure by the algorithm. And then repeat that until finally all vertices are in the tree, and observe that each iteration indeed adds one edge and one vertex that is connected by the tree, so that the algorithm will run in linear time, a linear number of iterations. Well, not linear time, but a linear number of iterations, because we still need to analyze the cost of every single one iteration. Let's illustrate that with an example, and that's going to be all for today. And next time we're going to consider an alternative algorithm that follows another approach and another paradigm in the calculation of a minimum spanning tree. So here you see a graph, and here you see edge weights assigned to the weights assigned to the edges of the graph. And let's consider an example run of Prim's algorithm on this graph, starting, let's just say, at this vertex. So what will Prim's algorithm do here in the second? It will consider all edges that consider the tree. Initially, the tree is trivial, right? This is a tree. All edges that connect the tree to vertices that are not yet in the tree. Which edges satisfy that property? This edge does, this edge does, and this edge. These are the neighbors of the tree. Well, in this case, the neighbors of the vertex, but there's just an initial part of the tree. In general, we consider them edges that connect the tree to its neighbors, and these are these three edges. And among these edges, it will choose the one with minimum weight. This is this one, right? It has less weight than these two. So it will consider this weight and add the edge and its connected vertex to the tree. So all other vertices are initially unreachable. And these are the distances from the tree to the other vertices as maintained in the data structure of the algorithm. So this vertex has distance 11 to the tree, because that's the edge weight. This has distance 9, this has distance 6. And in the next iteration, the Prim's algorithm will choose this edge of least weight, and then add this edge and the vertex to the tree. And thus the tree has grown, now consists of two vertices. still far from spanning the entire graph, but this is definitely a minimum tree, well, in a sense. Now let's repeat that and adjust the distances of the vertices to this now grown modified tree, right? So for example, this vertex initially had distance 9 to the tree, but now that this vertex has been added to the tree, this vertex receives a improved distance of only 8 to the tree. Furthermore, now this vertex becomes reachable from the tree, which previously is not. So its distance will actually decrease from infinity to 10. Now this is what happened here. So that's the update of the distances of the vertices that are not in the tree to vertices in the tree. Okay, and now the next iteration. Choose an edge with least weight. Choose a vertex which is closest to the tentative yellow tree. And that's this one, right? This is the closest vertex. This is closest to the tree. This is further. This is even further. So this, the next iteration, the second iteration, this vertex and the connecting edge will be added to the tree, thus having grown the tree to now consist of 3 vertices. Okay. And now we need to again update our distances. So previously this vertex had distance 10 to the tree, but now that this vertex has been added to the tree, this vertex now becomes closer and receives distance only 1 to the tree. So that's where it's going to update. Also, this vertex was previously unreachable. Now it is reachable at distance 12. And also, right, this vertex is also updated. Previously at distance 11, but since this vertex was added, it now receives distance 3. Okay, that's all. Next round, again, pick the vertex which is closest to the tree, which this is this one. Add that, thus growing the tree. Larger part of the graph is being spanned, but still not all of it. And we need to update the distances. Here, this distance needs updating, and that's all. Next iteration, find the vertex which is closest, which has a minimum weight add, which is this one. Add it, grow the tree, and update the distances. This distance will need update. Previously it was 12, now it is 5. And this distance needs update. Previously it was infinite, now it receives 4. Okay, next iteration, which vertex will be added? You guess? It is this one, the least one, right? Add and update distances. So no update here, no update here. Add this vertex because it has least distance. No update happening. Then again choose the final vertex. Only vertex missing here. And here we are with a spanning tree, right? So after the execution of Prim's algorithm, we see indeed the tree has gradually grown to cover larger and larger parts of the graph. And finally, it indeed spans the entire graph. And also the edges that have been added with together with each new vertex are edges of least weight. And so it seems intuitive that it indeed calculates a minimum spanning tree, but rigorous proof is not part of our lecture today. Time is up. So to summarize, today we've discussed several algorithms for the quantitative connectivity problem, ST connectivity, S to everything connectivity, and all shortest path connectivity with strictly positive edge weights. And we've considered minimum spanning tree problem, its specification, and we've seen Prim's algorithm for solving the problem, what remains, is to prove the correctness of Prim's algorithm. What remains is to analyze the computational cost of Prim's algorithm. What actually also remains is to turn this meta-algorithm on a very high-level description into an actual algorithm, because as you can see again, here there are some advanced operations that are not realistically to be considered as primitives, namely how to find the minimum weight edge among the remaining edges, and how to add it, how to transfer it to the tree. This is something we'll discuss in the next session. So thank you all very much for your attention, and see you next time.